Okay, welcome back. Today is the third day of um, in school or not in school learning, or learning through online, however you want to call it, remote learning. This is going to be our third day of this. Today we'll be looking at Taylor series. Now there are a few questions that y'all might be having about the whole format. Yes, I am giving homework every night, but it is due on Friday, kind of like how we did in class, where I'd really only check once a week. That's the whole idea here, is just making sure you're actually doing the work and get it all submitted by Friday, end of day. The quizzes will be posted on College Board every Friday, and so I'll make sure to update y'all on its learning whenever that happens. And make sure you're taking advantage of the Zoom tutorial sessions. Those happen every day, either at 11 o'clock or 1 o'clock. I take an hour-ish break for lunch, and then I'll come back and answer more questions, things like that. Please note that the Zoom sessions are for the previous day's lesson. So this video goes with Wednesday, March 25th. And that means the Zoom session for it will be on Thursday, March 26th. Okay? So make sure you keep that in mind as you're doing it. All right, so let's start looking at Taylor series. 2 lessons ago, we talked about Taylor polynomials for a function. Today, we're going to look at Taylor polynomials expanded out so that they become a series. So we were truncating our series to end at a certain point. Now we're saying, okay, we're going to take that series and do it to infinity. So we looked at a Taylor series centered at C on the first day of these video lessons. And so it's this formula right here. F of C, that's going to be a numerical value. F of C times x minus C, where C is the center and x is the variable. And then we keep going on. The second derivative of C times x minus C squared over 2 factorial. On and on and on until we get the nth derivative of C times x minus C to the nth power over n factorial. And that can all be written as a nice little sum here from n equals 0 to infinity. Okay? So, let's start with this first one. Find the Taylor series for f of x equals e to the 5x, centered at c equals to 2. Give the first 4 non-zero terms and the general term. So, what we're talking about with the first 4 non-zero and the general term. These that actually show up, that aren't 0, are your non-zero terms. This part right here is what we call the general term. We're not looking for the summation yet. Granted, once you give the general term, you could write it as a summation easily. We're just looking for the first 4 non-zero terms and the general term. Okay? So, looking back at what we need for this, we need our derivative. If we're looking for the first 4 non-zero terms, we'll start by trying to do our derivative 3 times. So we have the original function, first derivative, second derivative, and then one more for the third derivative. And so that should give us 4 terms. Now, if any of those give us 0, we're going to have to add more terms. But we're going to start by doing this with just 4 derivatives. Okay, so we start with f of x, which is equal to e to the 5x, f prime of x, which is equal to 5e to the 5x, f double prime of x, which is equal to 25e to the 5x, and then the third derivative of x, which is equal to 125 e to the 5x. So there are 4 derivatives, and remember, when we're looking at this formula, we don't just need the derivative, we need that derivative with our center plugged in, and it tells us our center is equal to 2. So we need to turn this into f of 2, which is going to be e to the 10th, and then I'm not going to rewrite it every time, but this is 5 e to the 10th, 25 e to the 10th, and 125 e to the 10th. This part is no different than when we were doing Taylor polynomials. Same exact thing we're looking at here. And And so we're going to set it up like when we did our Taylor polynomial. So we have f of c, e to the 10th, plus f prime of c, 5 e to the 10th, times x minus c, so x minus 2, plus the second derivative at c, so 25 e to the 10th, over 2 factorial, times x minus 2 squared, plus then our third derivative, 125, and I'm running out of room, so bear with me here, e to the 10th over 3 factorial times x minus 2 cubed. Now, that is the first 4 non-zero terms. None of these give us 0, so those are them. Now we have to also add our general term, so plus dot dot dot, and I ran out of space on one line, but we're going to create our general term. So let's look at what happens. We have an e to the 10th here in every single one, so that will stay constant. Okay? If we look at our leading coefficient, oh man, this should have been 25. There we go. If we look at a leading coefficient, it starts with 1, 5, 25, 125. Well, that's just all the powers of 5. So this is 5 to the n power. Because when n is 0, we get 1. When n is 1, we get 5. N is 2, we get 25, and so on. Then we have this right here, the x minus 2. If we notice, the x minus 2 follows the same power that the 5 did. So we originally have 1. Then we have x minus 2 to the 1 power, x minus 2 to the 2 power. So we have x minus 2 to the nth power over, and now we just need our denominator. So we have the factorials down here, and so we have over 1, over 1, over 2 factorial, over 3 factorial. Well, if we notice, we have 1 and then 1, so that means it starts with 0, because 0 factorial equals 1. Then it goes to 1 factorial, that also equals 1. Then 2 factorial, and then 3 factorial. And so we have on the denominator just n factorial. And so this turns out to be our general term. So in total, we have our first 4 terms and our general term. Okay, I know it's a little messy and it's a lot of work, but it's pretty straightforward. There we go. Now, we're going to look at our 3 special types of Maclaurin series. These are 3 that you have to know because they have common patterns. They're ones that you're going to see over and over and over. So, for example, if we wanted to derive a series for e to the x, we'd go through the process of creating a Maclaurin series. Now, once again, remember, a Maclaurin series just means it's Taylor, but c is equal to 0. Okay? So it's Taylor series with c equal to 0. So we have f of x is e to the x. And this should be a super quick one. F prime of x is e to the x. F double prime of x is e to the x. And then we need these with the actual value plugged in. So we're going to actually plug in 0 here. So I ran out of room. So this one, when we plug in 0, gives us 1. This one gives us 1. This one gives us 1. All right, because we actually have to plug in our c. And now we can start creating this series for it. So we have f of c, that's 1, plus f prime of c, which is 1, times x to the 1 power, plus f double prime of c, which is 1, times x to the 2nd power over 2 factorial. And this should be one that we don't need to do many more terms than this to be able to see what's happening. If we look at it, we see, oh, it's 1, x to the 1, x squared over 2 factorial. So this just becomes x to the n over n factorial. All right? Now the other thing we need to talk about is the second part. There it is. And if you did yesterday's homework, you should have been able to see this. Because problem 2 had this should have been set up so where you can solve for where this, or what values of x this equals e to the x. And you see that for all values of x, this will equal e to the x. So as long as you use this series, it's a perfect approximation. Now, it's only perfect if we use that series to infinity. So that leaves some problems that we might have in the future. Okay? But it is a perfect approximation for all those terms. Okay? Let's look at the next one. The next one that we need to know is sine of x. This one's going to take up a little more space, mainly because as we do our derivatives, so we have f of x equals sine of x, f prime of x is cosine of x, double prime of x equals negative sine of x, triple prime of x, the third derivative, equals negative cosine of x, and then over here we'll do the fourth derivative, equals back to sine of x. But the problem is, because we're doing a Maclaurin series, we have to center it at 0, which means we need to plug in 0 for these. Sine of 0 is 0, cosine of 0 is 1, sine of 0 is 0, negative cosine of 0 is negative 1, sine of 0 is 0. Right now, these two derivatives right here, this one, or these two terms right here, will just give us 0, and they'll cancel out. These three, actually. That means we only really have two terms in our series, that one and that one. So let's do one more. Let's do one more derivative just to see what we get. Granted, you should be able to see it pretty easily. There we go. So the fifth derivative of x would give us cosine of x. And this one, when we plug in 0, okay, we get 1 again. Well, now we actually have enough to set up our whole series. Now, I'm going to start by writing a lot, and then we'll simplify it down in the actual box. We start with f of x, or f of c. Well, f of 0 is 0, plus f prime of c times x, so 1 times x, plus f double prime of c times x minus c over x minus c squared over 2 factorial, but this is just 0, so 0 times anything is going to give us 0, plus the third derivative of c, so negative 1 times x minus c, but remember x minus c is just x cubed, that's cubed, over 3 factorial, plus the fourth derivative of c, well, that's 0 again, so that's just going to give us 0, plus the fifth derivative of c, which is 1, times x to the 5th power over 5 factorial, plus dot, 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 dot. Okay, now we're starting to see some things. We start to see this little pattern emerge of, okay, it's only going to be the odd powers. Okay, we're not going to do anything with the even powers of x. It's only going to be the odd factorials. We're not going to do anything with the even factorials. So up here in the corner, I'm going to start creating our general term. We've talked about this before, but if we only want something odd, that means we're going to use 2n plus 1. Okay, so when we plug in 0 there, we get 1. That'll be the first one. When we plug in 1 there, we get 3. That'll be the second one. 2 there, we get 5. That'll be the fifth one. Or third one, sorry. All right, over, and then we're going to be doing, oops, not 5. We're going to do the odd factorials as well. So 2n plus 1 factorial. All right, so that's 1 factorial here, then 3 factorial, 5 factorial. And then lastly, we have this 1 there that's alternating signs. We want it to be positive in our first term, negative in our second term, positive in our third term, and so we need to find the best way to do this. Now, if we look back up at the beginning, we saw, and I know my work's still there, we saw that we're using n equals 0 as our first term. We're using n equals 0 as our first term. So that means this first term here happens when n is equal to 0. So that means this should be negative 1 to the n power. So that we get a positive 1 when n equals 0. So this whole thing will give us our general term for this series. So we have x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, x to the 7th over 7 factorial, on and on and on and on and on, until we get negative 1 to the nth power over x to the 2n plus 1 over 2n plus 1 factorial. And once again, if you did your homework from last night, problem 6, you'll see that this looks very similar, and we end up with the same range on there, the same domain on there. So for negative infinity to positive infinity, that's going to be equivalent. All right, the last one we're going to look at is cosine. I probably should have given myself some more room here, knowing that I can't write very well. But this one should go quickly because it's very similar to what we just did with sine. So we have f of x equals cosine, f prime of x equals negative sine, second derivative of x, negative cosine, third derivative of x, sine, and fourth derivative of x is cosine again. Now this time I'm not going to do any more because look, we have 3 terms that work for us. That's 1, 0, negative 1, 0, and 1. So we have terms that work for us here. And what we'll notice is this is going to end up looking very similar to sine series. The only difference is instead of using the odd terms, we're going to use the even ones. So we have f of x first, so that's 1, plus f prime of x times x. Well, f prime of x is 0, so that's just 0, plus the second derivative of x, which is negative 1 times x squared over 2 factorial, plus the third derivative of x, that's 0 again, plus the fourth derivative of x times x to the 4th over 4 factorial, plus dot 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 dot. Okay, so it looks very similar, except now we're using even, which means our formula is going to look, our general term is going to look very similar, except instead of using the numbers for even, we're going to use the numbers, or instead of using the numbers for odd, we're going to use the numbers for even. So 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial plus on and on and on and on and on. And we end up with negative 1 to the n. That's still the same. We want the first one positive, second one negative. And we go to x to the 2n over 2n factorial, because 2n will give us an even term every time. And once again, this one will be the same from negative infinity to infinity. So these are the 3 important series you need to know. These are the 3 series that you should be able to come up with no matter what. You should not be having to go through and deriving them every time. You should just know that cosine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and so on and so forth. Okay, these should be things that you just know. Okay, now with these series, we can actually manipulate them to be different things. We're going to look a lot more in depth at manipulation of series tomorrow or in the next video, but we can manipulate them. So like for example, for this one right here, we have sine of x squared. Well, we just found sine of x. This x squared is just being plugged into there. So we know sine of x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial plus dot 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 negative 1 to the n times x to the 2n plus 1 over 2n plus 1 factorial. That's what we just found. Well, what we're doing here is we're just plugging in x squared. So that means this is going to be x squared minus x to the 5th over 3 factorial, because that is x squared to the 3rd. Oops, not x to the 5th, x to the 6th. I don't know what I am doing it, guys. X to the 6th over 3 factorial. Oops. Plus, then we have x squared to the 5th, which is x to the 10th over 5 factorial, plus dot dot dot. We still have the negative 1 to the n, that doesn't change. And then it's x squared to the 2n plus 1, which changes it to x to the 4n plus 2 over 2n plus 1 factorial. And there's our new series and our general term. So first 4 non-zero terms. I should have one more non-zero term here. That's on me, didn't read the instructions clearly. So let's go ahead and add one more non-zero term there. So we have minus x to the 14th over 7 factorial. Because the next term here would have been minus x to the 7th over 7 factorial. Okay, I don't know, I ran out of space a little bit there, but that is the whole idea of that type of problem. We can also use this to take derivatives. So now that we have a function for this, we can actually take the derivative of it. So I'm going to leave just this part here, just the part we want. So we'll get rid of all this. So we can now take the derivative of this. So f prime of x is going to equal, well, we bring down the 2, and then 2 minus 1 just gives us x, minus bring down the 6, and then 6 minus 1 gives us 5 over 3 factorial, plus, oops, seems like I erased some things I needed. That's 10, that's 14. Bring down the 10. There we go. Bring down the 10, and we get 10x to the 9th over 5 factorial, minus, bring down the 14, x to the 13th over 7 factorial, plus dot dot dot. We still have the negative 1 to the n, that doesn't change. The 2n plus 1 factorial doesn't change. Alright, but we do need to do something with this power. We're going to treat it like a normal power of x. We're going to bring down the power. So bring down 4n plus 2. Okay, and then times x to the new power. Well, the new power is this power minus 1. So 4n plus 2 minus 1 gives us 4n plus 1. And we can look back and make sure that works. If we plug in 0 here, so this is n equals to 0, that gives us a power of 1. This is n equals to 1, that gives us a power of 5. So this matches with what we end up having here. And so this is our derivative for that Maclaurin series. So this is just to show that after you find these, or once you know these general Maclaurin series for sine, cosine, and e to the x, you can do different manipulations with it. So go ahead and pause the video and try A and B here. Okay, welcome back. So now we're going to look at finding a Maclaurin series for f of x equals to x cosine of x. Give the first 4 non-zero terms and the general term. So we need to start by finding what cosine of x is. But we already know this one. This is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot 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 plus x to the, oops, not x, negative 1 to the n times x to the 2n over 2n factorial. Okay? Oops, that's a really ugly 2n factorial, but you know what I'm talking about. Okay? So this is the series we came up with earlier. Now we're going to create x cosine of x. Well, all that's asking us to do is take x and multiply it by our series cosine of x. Well, this is our series cosine of x, so let's multiply in x. We get x minus x cubed over 2 factorial plus x to the 5th over 4 factorial minus x to the 7th over 6 factorial plus dot 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 plus negative 1 to the n stays the same, 2n factorial stays the same. The only thing that's changing is we're multiplying in a new x right here. Well, x times 2n, or x to the 2n gives us x to the 2n. Oops. 2n plus 1. And there's our new general term. We can also take the integral of this now that we have it. So I'm going to go ahead and erase this just so we're not getting confused with what I'm doing. We can take the integral from 0 to x. Well, when we plug in 0 to all of these, we're just going to end up getting 0, and our constants are going to cancel, so it might be easier just to show what we're doing. We're going to do the integral from 0 to x of x minus x cubed over 2 factorial plus x to the 5th over 4 factorial minus x to the 7th over 6 factorial plus dot 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 plus negative 1 to the n x to the 2n plus 1 over 2n. Oops, forgot the factorial there. That's what we're going to be integrating, dx, or dt. Oops, that's bad. These should be t's. Ignore that. But all that says is that we're going to integrate this, and then we're going to plug in the x. So the integral of t is t squared over 2. Integral of t cubed is t to the 4th over 4, but then we still have that 2 factorial there, plus integral of t to the 5th is t to the 6th over 6 times, once again, forgot a factorial, 6 times 4 factorial, minus integral of t to the 7th is t to the 8th over 8 times 6 factorial, plus dot dot dot, negative 1 to the n stays the same, 2n factorial stays the same, but now we're going to add 1 to the exponent and divide by our new exponent. So adding 1 to this exponent gives us t to the 2n plus 2. Dividing by our new exponent is dividing by 2n plus 2. And then we're doing this from 0 to x. Well, the upper bound is just x, so we're just going to plug in x to all of these. And the lower bound is 0, but when we plug in 0, this all just gives us 0. So our integral is just x squared over 2 minus x to the 4th over 4 times 2 factorial times there, plus x to the 6th over 6 times 4 factorial minus x to the 8th over 8 times 6 factorial plus dot dot dot, and I'm running out of space here, -1 to the n over 2n plus 2 times 2n factorial times x to the 2n plus 2. And there's our final integral here. Pretty long integral, but it's doable. Oops. So let's keep moving. All right, this is the second part of today's lesson, which is really just looking at why we want to do this. Well, right now, we don't really have a way to do sine of x by hand. Like if I asked you to find sine of 1, it's not something you could do. But we could make this super accurate by doing a Taylor polynomial, or Taylor series, which we saw some when we started doing Taylor polynomials. Okay, so let's look at how accurate we can actually be. Use the Maclaurin series for sine to approximate sine of 1 so that the error in your approximation is less than 1 over 1,000 without using your calculator. Now that sounds like a pretty heavy task. We can't even use a calculator for it. What are we going to do? Well, remember, if we look at the Maclaurin series for sine, we notice that it alternates and it decreases. So this means we can use that alternating series test. Now, I know that was the last thing we covered, or one of the last things we covered before we went on break, but we can do it not for a check for convergence, but as an error bound. So we can say that as long as we get a term that is less than 1 over 1,000, then that means that's going to be our truncated part. That's going to be when we can cut it off. So let's see. If we're doing sine of 1, this is going to be approximately 1 minus 1 over 6 plus 1 over 120. See, that term is still bigger than 1,000, so that's not going to work. Minus 1 over and then 7 factorial. This is going to be the tough one. This is 120 times 6 times 7. So this ends up giving us 5,040, which means this term, this is less than 1 over 1,000. So that means this approximation of 1 minus 1/6 plus 1 over 120, that will approximate it with an error that's less than 1 over 1,000. And if you've already looked at part B, you can see that we're going to check to make sure that's the case. So let's see what this is equal to. It is approximately, I'm using 120, so we'll do 120 over 120 minus 6 times 20 gives us 120, so 20 over 120 plus 1 over 120. And this looks like this is equal to 101 over 120. So we're saying that sine of 1 is approximately 101 over 120. Okay? So 101 over 120. I just did it in my calculator. This is approximately 0.842. So we're saying that sine of 1 is approximately 0.812. And we're saying that this answer is within 1/1000th of the actual answer because of the alternating series error bound. All right, because of the alternating series error, we know, or we're saying that this is less than 1 over 1,000. Let's check to see if we're right. So let's see. I want to just hide this page. All right, there we go. So we're trying to figure out the actual error. Well, to figure out the error, we need actual minus approximate. That's how we're going to figure out the actual error. Well, the actual would be just whatever sine of 1 is, and our approximate was 101 over 120. Well, sine of 1, let me get my calculator again, and make sure we're in radians, not degrees. So sine of 1 minus 101 over 120 gives us, and the absolute value of that, gives us 0.000196 is what I'll round it off to. 196. Let me say approximately there. So that means our error is 0.00196, which is definitely less than 1 over 1,000. So we were able to approximate sine of 1 with a pretty surprising amount of accuracy. Okay? Let's move to the next problem. I want you all to try this one on your own. Okay? So go ahead and pause the video and try it. Okay, so let's look at this one. This time we're finding a series, or find in series form, an antiderivative of sine of x squared, and then use it to approximate the integral from 0 to 1 of sine of x squared, so that the error in your approximation is less than 1 over 1,000. Well, we actually already found the series for sine of x squared earlier. We did that in the previous part of the video, so let's go ahead and use that. Sine of x squared is equal to x squared minus x to the 6th over 3 factorial plus x to the 5th over, or not 5th, oops, x to the 10th over 5 factorial minus x to the 14th over 7 factorial plus, and we'll try with 4 terms first and see if that's accurate enough. If not, we'll come back and try it with something a little more accurate. Okay, this should have been 6. It almost looks like a 5. Alright, so now we're going to be taking the integral of this. So the integral from 0 to 1 of sine of x squared. So we need to take the integral of x squared, that's x cubed over 3, minus the integral of x6, that's x to the 7th, over 7 times 3 factorial, plus the integral of x to the 10th is x to the 11th, over the 11 times 5 factorial, minus the integral of x to the 14th, so x to the 15th, over 14 times 7 factorial, plus dot, 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 dot. Alright, keep going on, and we're going from 0 to 1. When we plug in 0 to all these, we just get 0. But when we plug in 1, we get 1 over 3 minus 1 over 3 factorial times 7. That's 6 times 7, which gives us 42. Plus 1 over 11 times 5 factorial. 5 factorial is 120. 11 times 120 ends up giving us 1320. So we actually don't even need to find this one because this is still an alternating series, but this term right here is less than 1 over 1,000, which means we only need these 2 terms to approximate this integral. Alright, so 1 over 3 minus 1 over 42 is 1 over, or it can be changed to, one second, 14 over 42 minus 1 over 42. So this integral is approximately 13 over 40. Oops, not 140. 13 over 42. So that's what we're saying is our approximation. And we're saying it is within 1/1000th of the actual answer. All right, so now let's use our calculator to figure out the actual answer. And this is where having your calculator becomes really important, because we're saying that it's going to be the actual, or the integral from 0 to 1 of sine of x squared dx minus our approximation, which was 13 over 42. I keep putting 142. 42. We're going to see what this error was. Okay, so I'll give you a second to put that in the calculator. You can pause the video while you do it, and then we'll look at it together. All right, so this should end up being approximately 0.00074, I think. Let me double check that real quick, because now I'm forgetting my... Yes, 0.0007444 technically. Okay, and so this is definitely less than 1/1000th. So we have an error that is less than 1 over 1,000. Now remember, this only works because it is an alternating series. If this wasn't an alternating series, we wouldn't be able to find this error so easily without a bunch of trial and error. Right? Last problem we're going to look at. This is a little bit different one. Yeah, I don't think we're going to do this last one because we're pushing a lot of time right now. We're going to look at this one. Write the Maclaurin series for f of x equals e to the x. Give the first 4 non-zero terms and the general term. Okay, so we're going to do the Maclaurin series for e to the x. We've already done this. This should just be 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus ... That's the first 4 non-zero terms, plus x to the n over n factorial. There's our Maclaurin series for e to the x. Now we're going to look at the next part of this problem, which says use that answer to find this limit. So that means we're saying the limit as x approaches 0 of 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus ... That's the f of x part. And then it's minus 1 over 2x. Now, this is where things get a little interesting. Because if we look at it, we end up with this one and this one canceling out, and so we can't just plug in 0. If we plug in 0, we end up with 0 on the top and 0 on the bottom. So we're going to have to do L'Hopital's. Okay? And so now, when we do L'Hopital's rule, we have the limit as x approaches infinity of, and we end up with just 2 on the bottom, and on top, this becomes 1, this becomes 2x over 2 factorial. We could simplify that, but we'll see in a second that it's not going to matter. 3x over 3 factorial plus ... Well, this time when we plug in 3x squared over 3 factorial, this time, and I put x to infinity there, that should be x to the 0. This time when we plug in x to 0, we see all of these go to 0, and we're just left with 1 over 2. So, we found that the limit is 1 over 2. Now, some of you might be like, well, you might be wrong. How can we trust this? Well, let's actually check it with the actual answer. So if we did this with the actual original equation of e to the x, we have the limit as x approaches 0 of e to the x minus 1 over 2x. We can do L'Hopital's rule here, because if we plug in 0, we have 1 minus 1 over 0, and that's 0 over 0. So the limit as x approaches 0 of e to the x over 2, and lo and behold, when we plug in 0 here, we end up just getting 1/2. So just showing more things that we can do with these series approximations. Okay, this last one here is a little tough. I'll make sure to write the answer for y'all to check it. It will take actually multiplying out 2 very long series. So I will take a screenshot and post the answer here, or I may just write it here at the end. I'll probably pause the recording, write it so you can check it. But for the most part, this is the end. Make sure you're doing the homework. If you have any questions, come to or join in the Zoom session tomorrow to ask any questions. Remember, there's one at 11 and one at 1. All right, you have a good day. Never mind, I took this question off of the homework, so you don't have to worry about it. So, on your notes, ignore this problem. Thanks, y'all have a great day.